So we will be now implementing different techniques to control the randomness in our text generation. So one of these techniques is called temperature scaling. So in this section, I will conceptually explain how a temperature scaling works. And then in the next section, we will introduce another technique called top K sampling, and we will see we can actually combine those techniques. And once we have both techniques, we will actually go back and modify the generate text function. But for now, just to make sure we understand how temperature scaling works, I wanted to work with a smaller example. So for that, I prepared a smaller vocabulary where we only have 9 tokens. Before, we worked with a vocabulary of 50,257 tokens, which is a bit hard to track if we want to print out results and look at plots. So for this example, we are looking at this small vocabulary. And I will also create the inverse vocabulary similar to chapter 2 so that we can map backwards from tokens to words. So it's essentially just the same thing flipped. I also prepared some sample logits. So these logits would technically be created by the model by calling the model on the inputs, but yeah, to keep things a bit smaller, self-contained, and easier to follow, I just took the liberty and made up some values here. They would, in theory, be generated by a model by passing inputs to the model, but I want to keep things simple here. And we can see there are different values, and we can see there are medium-sized values, very large values, very small values, and so forth. And we could technically work with these logits directly, but we will apply the softmax function to convert them into probabilities. Let me just, before I stumble upon my keyboard here, copy this. So here we have the probabilities from the softmax, similar to what we have done before, given these logits. And we can see these are like now the probability values associated with these logits. So we see this is a very small value. So E minus 0.02 means 0.06. And then here we have a pretty large one. This is 0.57. And here we have 0.35, very small value, 0.00013, and so forth. So there are different probabilities for each of these tokens. And if you recall the way we used or we sampled, for example, if I do next token ID, the way we sampled, we used the argmax, and we used the argmax on the probas. Let me just return this as an item. If I do this, this should give me the probability or the position where the highest probability is located. So 3, I can count 0, 1, 2, 3. Makes sense. This is the largest value here. This is 0.57, a 57% probability. And token number 3, I can actually look this up maybe in the inverse vocabulary. So next token ID. Oops, somehow pressed the wrong button here. There we go. It's forward. So forward token ID 3 is the next generated token that the model would generate with our generate text simple function. And and so that is deterministic. No matter how many times we execute this argmax, this is always the highest probability. This will always be selected as the next token that is generated by the model. Now, what we can do is, there is something called torch multinomial. And torch multinomial lets us sample from these probabilities here. So instead of deterministically always getting the largest token, we will now get the token proportional to these logits, or proportional to the probability values. So this means if we do it like this, 57% of the time this token gets sampled, and 35% this token gets sampled. And then 0.001% of the time this token gets sampled. So to show you what I mean, I can execute this and it gives us forward because yeah, it's the most likely token. So most likely this will be returned. If I disable the random seed for a moment, if I execute this again, I see forward is returned again. Let me do it one more time. Now I can see actually a different token is returned toward. So toward it's token number 7 corresponding to 0, 1, 2, 3, 4, 5, 6, 7 to this one here. So occasionally it will generate toward and occasionally it will generate forward because it's proportional to these probabilities. So now we added a bit more creativity or randomness to our model, and it is not totally random, right? Because it's still depending on these probabilities, and these probabilities get learned from the training data. So the model, how it learns, it's learning to generate the next token in a given text, where the given text is the training data, and there could be different combinations of words occurring. There could be a sentence that says every effort moves you toward your goal or moves you toward something. And there could be a sentence, every effort moves you forward. It could be a sentence itself. And so depending on how frequently these word combinations occur, the model will learn these probabilities. And some of the time, or some tokens are more likely in certain positions than others. So it's still just statistics. It will just, be based on the frequency things occur in the training data, essentially. But at the same time, we don't brute force always return the most likely token. We sometimes also add, or we have this little freedom here to sample from all the tokens. But we make sure that the model doesn't generate nonsense by weighing them or having a weight that depends on the training data statistics. Because if we would do it totally randomly without weighing these probabilities, then the model will again generate gibberish where all the tokens are equally likely. So we have this kind of like common sense based on the training data that more likely tokens will be more likely sampled. And so this is one way we can generate these more, I would say, creative texts, or not just memorizing from the training data. By the way, instead of just brute forcing here, executing this, I can also, I have a more sophisticated function here. I can also just repeat this 1,000 times. So what I'm showing you here is a function where I call this torch multinomial 1,000 times, and I just save the results, look at the frequencies, and then just print them out. And so you can see 582 times out of 1,000 it prints forward, 73 times closer, and 343 times toward, and even 2 times inches. So yeah, so you can see it is not always generating the same tokens, and we can further influence this. So this is just based on the probabilities, but there's a common technique called temperature scaling where we modify this distribution further. So I will make a function called softmax with temperature where I will apply this temperature scaling to change this distribution a bit. So how it works is what you're looking at here for now is nothing new. This will be like the regular softmax. So we have the logits, then we have the scaled logits where I'm just dividing the logits by a number. Here it's a 1. And so if we divide a number by 1, nothing happens, right? 5 divided by 1 is still 5, or 0.5 divided by 1 is still 0.5. And so here nothing new happens. So we just apply the softmax like we did before. But now if I replace this one by a different number, I call this the temperature, I influence the values of the logits. I make them either smaller or larger, and that will then affect the softmax. So this is helping us kind of as a hyperparameter, the temperature, to change the distribution here. So I, as an example, I can consider, let me execute this. For example, the temperatures 1, 0.1, and 5. So here 1 will not do anything. This is like I showed you before. It will just divide by 1 and nothing happens. 0.1 will make the logits larger, right? So it will So for example, if I have 10 divided by 0.1, it will be 100, right? Oops. So we'll make the logits larger, or we divide them and make them smaller, right? So by that calculation here, we are influencing the logits, and then we will get different softmax values. So smaller values here, they will essentially result in larger peaks, right? Because we make the logits larger, and the larger the logits, the larger the softmax values. And if we divide by a larger number, we make the logits smaller, which will make the softmax also smaller. It will distribute the softmax more. Because in the softmax function, remember, we have the constraint that they still sum up to 1. So if I go back here, and I type probas.sum, you will see they sum up to 1. And it will be still true here, because everything that comes out of the softmax, I mean, by nature, by design, by this function, will sum up to 1. So if we make some values larger, the other ones will be correspondingly smaller. So let me show you actually in a visual how this will look like. So if we have these temperatures and we compute the softmax here, so what I'm doing is I'm applying this function to the logits we had, to the logits up here, right? So I'm applying this with a different temperature for these 3 temperatures. And then we get these scaled probas. So let me just show you the shape of this. So this is 3 scaled proba values. Oops. It's a list actually, sorry. So we have 3 probability tensors, where the first one should be corresponding to our original probas, because we haven't modified anything. It's just dividing by 1. But then when we have this one, oops, this is with a temperature of 0.1, and we have this one, we can see these are different. Now these are kind of closer to each other, and these are more peaked. You can see some of them are very small and some of them are very large. So this is a 99%. So I actually prepared also a plot so we can look at this more visually. So this one is just plotting these out as a bar plot here, and you can see on the y-axis the probability values you saw here, and then for a temperature of 1, which is the original probability values, you can see we get about 57% of the time we get forward, we get 35% of the time toward, and then with a smaller probability closer. But now if we make the temperature smaller, 0.1, this will be a more spiked distribution. You can see these large peaks here. At forward, it's 99%, and a small one at toward. So if we go here, we have 0.09% for toward and 99% for forward. Now, if we make the temperature larger, we make them 5, you can see the distribution becomes more uniform. So the values are more closer together, because each of them, they still sum up to 1. So that's one constraint, right? So if we make some values larger, some other values have to become smaller, right? So that's like the constraint we have. And with that, we implemented temperature scaling here. And this is one technique we can further control these values, how often each of them gets sampled.
Get this book at Manning.com.